welcome back. So we have finished off MM1, MMM and MMMM. So what is next to look at is this queue with finite buffers. In general, any MMM queue can have finite number of buffers, but MMMB you can write the equations for that, but it's not really closely, or it's not a closed form solution. So we don't have that. We can write. So for to look at the MB system, where B is greater than M, otherwise it right. And B less than M also does not make sense because you have more servers and not enough people floating around, right. So we will assume that B is greater than M, and B represents the total number of customers in the system, that is the upper limit. So that includes the one in service, right. So that implies there are B minus 1 buffers, right, to hold packets while the one is being serviced. The ones, as it is MMM, so we will have more than one customer who can be serviced. Okay. So to again we go back to our standard, right. Set of Markov set of states, lambda, and then the reverse is of course mu, 2 mu and all that. Okay. So we can write the Pns as before, simply the product, right. So only difference is that now the set of states is going to be, so your this summation, right, Pn, only that will vary. So Pn 0 n equals 0 to B equals 1, that's the only difference. Otherwise the equations are going to be the same as we saw for the MMM case. So we will only look at the MM1B for specific results, right, for the analysis part. So for the MM, no, there is only M servers in the system. So past M, the return rate is always mu. Okay. All right. So this one is as usual. Okay. So the representation for the system is that there are a total of B minus 1 slots here, then there is one more guy, right, who is getting served here, and then the system basically leaves. So in an MM1B system the packets will keep arriving, but there is a non-zero probability that the packets arriving will get dropped, right. So therefore the effective arrival rate will be less than lambda, but as far as packets coming into the system changing states, the rate is still lambda. We will look at the effective arrival rate in just a second, right. So in addition to all the other things we have this extra parameter to compute called the blocking probability, right. This is the probability with which an incoming packet is dropped. Okay. And this of course is servicing at mu packet.
So it will be same as PM.
It will be same as PB. PB.
The PM which we are calculating n is equal to 0 to b.
Yeah, just like that. Yeah. So we will compute the rest of the derivations will be exactly the same. There is no change. Right. So this will be the same set of equations. The only difference is the normalizing equation will be different. So now what is Pn? We do not have to really derive that. We have done this enough times now, right? Simply rho n, where rho equals lambda by mu. So that is simply that. And this is only difference is that for n less than or equal to b or equal to 0, it is defined it is 0 anywhere else. No, n can be 0 also, p 0. Oh, okay, well n goes to 0. So to be really picky, okay, we will make that. And then your okay. So this is why my use of this one if you want to. So it does not matter that n is the summation goes from n equals 0 to b, and this is our high school geometric series, right. So we know the formula for this one. So the P naught is fairly easily derivable. So for this, should rho be less than 1 or equal to 1 or greater than 1, does it matter? It does not matter, right, because it is going to converge whatever be the value of rho. So therefore that restriction on rho is gone. What does it mean? It means that your system capacity is fixed. Arrivals can be as much as high as they want to be, arrival rate can be as large as they want, but the packet will simply get dropped. The only thing your PV will increase as lambda increases, right. Therefore this is the stable queue. So that this queue is technically stable. So what is that? So 1 plus rho plus all the way up to rho b. So there are b plus 1 terms. What is this?
1 minus 1.
1 by rho minus
Rho power b plus 1 minus 1.
1 minus rho power b.
Either way is fine. We will use this because we are. So whether you put rho minus or this one, right. If rho is greater than 1, then rho for b plus 1 makes sense, right. And actually if rho goes to 1, this is not correct. So this is only for rho not equal to 1, right. If rho goes to 1, then this is technically undefined, but that we can simply directly solve, that is 1 over b plus 1, right. So let us look at the rho not equals to 1 case. It will be simply b plus 1, so Pn's will be all 1 over. If lambda equals mu, then all the Pi's are equal, and all the Pi's are equal, there is only there are b plus 1 terms, so therefore each Pi, right. So for rho not equal to 1, this is defined, right, otherwise it becomes even simpler. Alright, so therefore P naught is, therefore is become totally messed up. 1 minus rho by so as an aside, for rho equals 1, all the right P naught equals P1. But this you can, if you look at the Markov balance equations, right, lambda P naught equals mu P1, so lambda mu is the same, or right, then rho goes to 1, so therefore they simply cancel out. So all the P is equal, therefore that's the only side. Okay. So now if you look at this again, if you plug in b equals infinity, right, so you can simply see that when rho is less than 1 and b approaches infinity, then the bottom factor denominator becomes basically 1, therefore it is 1 minus rho, and that is what we also derived in the case of the first system, right. So in general in an this system will the server be more idle or less idle for rho less than 1, MM1b will it be more idle or less idle?
More it.
More idle. Because your customers that are dropped, and finally when the queue is busy, the server is free, the customer who could have been serviced has already left the system without joining the system, right. So anyway, that by looking at rho and looking at since it is less than 1, right, the denominator will be larger in that case. Okay, those are just sort of secondary analysis, but this is your first expression, right.
The rho which we are calculating here lambda by mu, this is we are taking the arrival rate or the effective arrival rate?
This is a real arrival rate.
Real arrival
Which arrival rate is it? Because that is the rate of transition of your Markov chain, right, to go from one state to another state, right, you would be with that rate rho only, and you go to b, then the rho does not really matter, no packets will be admitted. Alright, so now what is the next thing to do? We need to compute the number of expected number of users in the system and all that stuff. Okay, so let us try that. So it is very similar to the MM1 except for this okay. Now what next? Again this is n rho n, so we always find that if it is n rho n, making it n rho minus 1 is better, right. And this is nothing but what we are trying to do is essentially 1 plus 2 rho plus 3 rho squared all the way up to b rho b minus 1, that is the summation that we are going to get the closed form for. And what is that going to be? So what is that value going to be?
Keep this here, then first differentiate into this like this. 1 minus so
1 minus
so called v by 1 minus rho divided by v only.
not the so
No, I'm just asking the formula. This is the formula. V square.
do some more versions of this derivation before I finally
This D is what this is. With respect to with respect to B. It will become 1 will get 0 minus B.
1 minus rho b plus 1 divided by 1 minus rho whole square.
1 minus rho b minus 1 and 1 minus rho plus b rho power.
Okay, let's write that. And next page. So what is your derivation?
Just multiply the series by rho.
Oh, I took out rho.
Okay, so you get rho 1 minus rho power b minus 1 upon 1 minus rho whole square plus b rho power b upon rho minus 1 on the right hand side.
I'll write
Minus
you are saying. Okay, let me just.
B
Okay. I. Well, this we know, right? So from this we should be able to derive what we want to do, right? So and what is this? And I am doing it with expansion because I tend to make mistakes otherwise. The same thing, right? So differentiate this thing. Actually, what? Yeah. So differentiate, and then you would get your right hand side, right? Differential of this is now what? Now tell me, right? So what's that on the right side? 1 minus rho into minus, so it's all so what is that simplified to? So that's 1 minus rho b plus 1 divided by 1 minus rho, and there is a, we will not actually, we will just leave it as it is. There is still a squared here. Did I get it right? So this is that summation, right? The partial summation that we are looking for. Then multiply this by P naught and rho, then we get our E of n, right? What happened? Did I miss something? B is, this is, I am just retaining this as it is. I am not split, I am just separating the sums, that is all. So b plus 1 to the rho power b, and then when finally will, is it correct? Because I have some 3 different derivations on my notes. I was doing this on the train, and then finally I ended up with one. it's not easy to derive when the train is moving. So what do we get? So this is now I'll write that whatever we had before, right? So that's so what's our P naught? P naught is by 1 minus rho, there is another rho, and then there is no. This was P naught, right? 1 minus rho by 1 minus rho P plus 1, then there is your rho, and then we had these two terms, right? This was the left part of the term, so we will just repeat this. Into plus B plus 1 this is finally what we end up with, yes or no? Am I the only one getting this, or you are also trying this? So finally we should look at something that is starting to get familiar, okay? So this is basically rho by 1 minus rho. What is that? That is E of n for infinite q. So will this be less or more than infinite q's, the number of customers? Should be less, right? So therefore that's why you have your minus sign here, and then what is that multiplicative factor? It is B plus 1 rho B plus 1 divided by 1, suppose. So therefore as B becomes smaller, then the number of customers also will become small, okay. So this is finally the E of n that I was looking for. So once I get E of n, I can then simply proceed deriving. I can also derive E of nq the same way, like we did n minus 1 into rho of n, right? Yep.
I'm getting only one term.
You lost a term. Should go back and check. We got those two terms because we simply, I just differentiated this, right?
Same procedure.
Okay, and then I just kept this term as it is. So I took this term out and put that in front, and then this is 1 minus rho gets cancelled out. So why would I have lost the term? Only two terms here.
One plus 1 I forgot.
Okay.
Did also.
It was the same only.
I did this. Then
So
I
that is the first expected number of customers in the system. So what is now blocking probability? What's the probability that the customers will arrive to a full queue? That's the blocking probability, or a full system, right? So what is that now? Basically probability of being in state B, PB, that's why it's PB here. So simply 1 minus rho right, Pn equals P naught into rho n, and P naught is the first part, this is P naught, and that is n equals B. So this is our blocking probability. So that is how we derive the probability of customers getting blocked into the system. So why is this useful is we usually try to do it the other way. We try to see what should be the buffer size to meet some target blocking probability requirements. You want to set the PV to be some value and then go backwards and say for this kind of arrival rate and this kind of service rate I should have at least this many buffers in the system.
But here our B includes M also.
So people who are getting
this is total
serviced.
customers in the system. Yeah, that's simplification. Otherwise there are B plus 1, that's all, right. If you don't include the one, it will be B plus 1, B plus 2 all the way to B plus M, but just to avoid confusion we said B includes all the customers under service, and therefore B is larger than M. Okay. So now how do we calculate the waiting time, response time? So the arrival rate, that is if you look at the system as such, customers are coming and they are getting chucked out, right. So only a subsection or subset of the customers enter the system. So what is that rate at which customers enter the system? What is the arrival rate for effective arrival rate? So this is basically E of n, but not lambda but effective arrival rate. Because only customers that see an empty spot can enter the system. So what is the rate at which, what is the rate for that? So effective arrival rate is, yeah, so we have seen, some of you have seen this just that, right. So probability PB you get kicked out, 1 minus PB you enter the system. So E of R is basically now simply that whatever expression that we saw before divided by lambda into 1 minus PB. Yep.
We are calculating on ER, EM.
Everything for Poisson arrival. Suppose we have got a deterministic arrival, the process will remain the same.
No. For GM1 or DM1,
Yes.
MD1 we have results, DM1 I do not know how to mention.
So for
Yes,
MD1
yeah.
there is a different.
For DM1 it becomes a discrete time event, right?
Yes.
Discrete time discrete time chain. Every instant of time you are going to get a packet, or every few instants of time you are going to get a packet. That you can model. Actually, you usually try to model that as. See, there are two things. One is your arrival instants are not there every instant, so you will have to translate the D into some sort of geometric X series that says that if I get for sure one packet every X over time, then you will have some probability of being in the same state in terms of arrivals, but the return can be Markovian, right? The return rate will be exponential. For MD1 we'll come to that. MG1 will come.
Same memoryless property only.
MG1 actually derivation we won't be able to do it today, but that is slightly different derivation is there. So in fact there is another system called semi-Markov models where you can use the same approach. If you are given the set of states and the set of probability transition matrix, you can exactly as this just derive the state visiting probabilities, the V's, and then from that if you know the sort of average waiting holding time in each state, then you can compute the steady state probability of being in each state. That we will look at when we look at this example for TDMA, how we can model TDMA using this. But TDMA can be modeled in two ways. One is MG1 with vacations, or MD1 with vacations, and the other is using a semi-Markov model that we will sort of go as we go through. We will look at it. Yeah, those things all will come up next, right? So we look at MG1, we look at MD1 results, then MD1 with vacations. That's also there, right? Where the server goes on vacations, right? After in between. So okay, so any questions about this set of derivations so far? So once I determine E of R, then the rest of it can simply follow suit, right? So what is E of W?
E of R minus 1 by mu.
The service time per customer does not change, right? That is still the same 1 over simply the total server response time minus the service time 1 over mu. This is the mean service time, right? All this, and then therefore likewise E of NQ is in terms of EW don't forget the 1 minus PV. Alright, questions on this basic derivation so far? So one example. Okay, so let us look at that lambda equals 100 and what was mu before 200, 0.5 utilization, right. Okay, so for a system D equal, we will make it 8, right. Calculate all the 4 performance metrics. So we will always try to find out P naught, right. Let us compute P naught first, we do not really need that because it is implicit in the E of n, but so what is the probability of system being idle? 5,009. And then what is the corresponding MM1 system values? P naught is rho is 0.5, right. So MM1 system idle is simply 1 minus rho, right. Rho is the server utilization. So this is point. And E of n was 1. Rho squared, so that is 0.5 by 1 minus rho, 0.5 into 0.5 by 1 minus. E of n
0.98.
point
98.
0.98.
23.
239.
Thank you.
0.5136.
0.5.
5136.
Okay.
The point
5136. Earlier.
by 1.98, that is E of n
We
cube.
earlier.
E of NQ is more than
Okay, this will be right. My PFB is wrong.
I got sir 0.98239.
E of NQ check. If this is 9.8, then E of W is 4.8.
Mine is wrong.
Point 4805.
Point.
4805.
This is 4.8.
This is 4.81.
That is okay. 4.8 milliseconds.
Okay. Okay. So if you had to use these numbers to your advantage, right, see these are the numbers that is reported. So what you find, E of n is less naturally, and because E of n is less, the delay is also less, in the average delay is also less in the system. So what is the best way to reduce delay in a system? If somebody says reduce delay in your system, right, simplest is to impose limit on the buffers, because as you have more buffers or less buffers, more packets will get dropped, so fewer customers get serviced, right. So sometimes you will see papers where they will say my delay is reduced in the system, and then you go and look at the throughput, how many customers actually are being serviced, that will be also correspondingly less, right. So less customers served, then you end up with having less queuing in the system, okay. So the easiest way is to simply cap that without having to increase your service rate or decrease lambda, simply imposing the restriction on B itself, because when your B reduces, your PB also will increase correspondingly, therefore less packets enter the system, right. Okay. So what would be the worst case delay in this queue? The MM1B system, what is the worst case delay?
So, I mean, a probability, we can't say a number, right? It can be as arbitrarily large.
I guess if it will be worst case would be infinity. So my B might be it will be the on average you will see, okay, if you are a customer that enters the system, then no, you can look at, okay, how do we quantify that, define the worst case? If you arrive the system to be, I need to define my delay, right. So on average what will be the largest delay that I will see if I enter the system? It will be okay, we will have to work out that definition again. Okay, let us try that. What the heck? Yeah, so you will be the last packet, and therefore you will see 1 by mu B1 to or B into B minus 1 into 1 by mu ahead of you, then you will see 1 by mu for yourself. Okay, so now let us try that. Let us try rho equals 10. For rho equals 10, what is E of n? And what is particularly delay, right? Because what would you expect in terms of with increasing rho, right, and with E of r plotted in this direction, this will naturally increase, right, as rho increases this will increase, but at some point it should simply stabilize, and that stability value would be, let us see if it is B by rho, right, should be 80 milliseconds, that should be the largest delay that you are seeing.
If you are writing the last packet in the buffer, then
Yeah.
only you'll have
Worst case delay, otherwise it will drop you.
Yes, only the thing is, if you really look at worst case, then everybody might have infinitely long times, right, and therefore you may end up having infinity into 8, but let us see with this what is coming, right. So with rho equals 10, what is the EFR? The only thing, the service time per customer is never, it's not finite, because your service is mu e power minus lambda x going greater than 0. So if you are really right bad, and if you look at the worst case as that, in that definition, all your customers might require close to infinity service, right, in which case you might be waiting for a very long time. So that is hard to quantify. So what we are saying is, under the heavily loaded system, what is the expected value would be the one. So my that is the way that you will have to. No, system will not be unstable. That is the whole thing with finite queues, right. For this is where rho equals 10, because what will happen is large fraction of the packets will never enter the system.
You cannot use this one now.
E of n is negative. You are also getting E of n negative.
So it's greater than 1.
Did you make sure that both the numerator denominator are both negative? Then You end
But
up
we
with-
cannot use the formula, na sir, because
You
that
can
is
use the
row less
formula.
than 1.
No,
No,
Yeah,
because
for-
that is row in less than 1 pe only you can
for,
even
for
use.
infinity you have maximum is 1, right? Yeah. So your system will never have E of n greater than 1, it will always be less than 1. It will approach 1 when no, when rho becomes, well no, let's see, okay, sorry, in this case
नहीं वो कैसे
No, no,
होगा?
I'm not-
वो
this
तब
is
होता है
MM1
ना,
B
rho
I'm
is less
talking
than
about.
1.
I am looking at MM1 8, not MM1. So it will be actually more, yeah, it will be greater than, yeah, it will increase. .8, right? So you will get about 7 point, so you will get 78 milliseconds as your EFR. Yeah, it will be greater than 1. Yeah, that's fine. So what is happening is your queue is getting to be full. So as rho approaches infinity, E of n approaches B, right? Then you can look at our formula itself and verify, right? Plug in rho equals infinity and see what happens. So infinity to the power b plus 1 divided by 1 minus infinity to the power, so you can just simply chuck that 1 minus business, right? And all you will have is rho by rho, which is 1, so you will have, yeah, you will end up with b. You plug in rho equals infinity in your E of n expression, right? And then rho by 1 minus rho is 1. No, infinity by infinity is 1, right? You forget that 1 minus rho factor, right? So remove that 1 minus in both expressions, you will simply have b plus 1 rho b plus 1 divided by rho b plus 1. So b plus 1 minus 1 equals b, except that minus will have to be appropriately dealt with, right? If rho is very large, then 1 minus rho will become minus rho b plus 1, that is all.
We are taking 1 minus rho, 1 minus rho. We can use rho minus 1.
Yes, we can do that,
Both
but
numerator.
whichever way you do, it will be done.
We change here also. Yeah. If you do like this, you will get minus here and minus here will get
Right, so so if I simply look at this expression and plug in rho equals infinity, right, what happens? 1 minus rho is nothing but minus rho, 1 is so small, so therefore, and 1 minus rho b plus 1 also becomes minus rho b plus 1, right? The rho is so large that the 1 minus makes no difference to it at all. So you will have simply minus 1 then plus b plus 1, everything else gets, and that is what we should be having, right? If the load is very high, then you will, all the slots in your system will be filled up. Agreed? I am sorry? That is fine, I have rho b plus 1, rho b plus 1, I can simply negate that. If rho is 1000 b plus 1 by 1000 b is 1, right? I am for, okay, for very large rho, whatever be that particular value of rho,
Like the general definition we said, like you are also having effective variable, right? So 1 minus PB will go to 0, then what will happen is EFR will actually go to infinity, normal definition wise.
by EFR will
Will go to
your-
infinity.
no, your no
It
system
will be b by lambda.
arrival into the system will be, your PB will be fairly large,
PB
or close to 1, yeah,
Close
so
to
it
1.
goes to almost 0, that's what it is.
EFR will actually go to infinity as rho goes to infinity.
What for rho equals 10, what happened to 1 minus, what was PB?
PB is there. We just put 78. That's wrong. That's what I'm trying to say. 78 into 1 minus PB should be the answer.
10 into 1 minus PB. Yeah.
Yes.
Oh, okay.
So
It's still saying
78
that
is
this will
It's actually will
for
go
the
higher.
customers entering the system.
For only the customers entering system, we can see response time will be B by lambda.
Yeah, this is only for the customers entering the system.
But
Yes.
though we can't call it EFR. It's called
No, this is the response time of the system for only the customers who enter the system, not the ones who arrive at are not serviced.
No, what's the
Customers who are not serviced are never going to, are not part of our. That's why EFR is only that using Little's law is only for the customers who actually enter the system.
effective arrival rate, na sir? What do you think?
Okay, all right, okay. So this is our.
You gave row, but you didn't give effective arrival rate, so
okay,
you cannot calculate.
Fine. Let's try that then. So let's verify.
formula because we said like we have to use the effective arrival
Okay.
rate.
Yeah.
Okay, so what is PB in that case?
But even if you calculate PB, we require lambda, sir. Lambda. What is the arrival rate to get effective arrival rate?
Yeah, in that the previous case. Oh, okay.
The other thing,
For the previous case, then if rho is 10, right, the same example you're talking about, your lambda is 2000.
then we can calculate, sir.
Lambda is 2000, right? So your lambda is fairly large. So now tell me what the 1 minus PB is.
Won't the effective arrival rate will be equal to rate of service?
Because since the number of users coming in, so
probability
as users get service,
1, right?
So your system is limited by mu. So lambda will basically be as good as
Zero.
rho equals 1.
This will become 0. So EFR will become 10.
Because your system is constantly removing. So basically, whenever there is one customer who is removed, another customer enters the system. Arrival rate becomes mu. So anything greater than mu, or actually not exactly mu, but when you try lambda rho equals 1, you will not get this right. When it's in a very large system where there is always instantaneous replenishment, as soon as one guy gets kicked out, another guy is immediately replacing that customer because your lambda is so large. Okay, so so what is PB in this for this rho equals 0.9, okay. So effective arrival rate is approaching 200. So that's now getting close to our mu basically, right. So it will be, so therefore E of R, but the 7.8 is correct, divided by 200, and that in the long range is B over mu, right. That is what we started saying, that when rho goes to infinity, your average delay for the system, when rho goes very large, will become B by mu. So your lambda effective arrival rate approaches mu, and your E of n approaches B, so it will be B by mu. So okay, so when rho, how about this? I won't say rho approaching infinity. Rho larger than 1. So basically lambda into 1 minus PB equals mu. So your PB becomes, that is what it becomes, right. Effective arrival rate becomes mu. So equals 1 minus rho, right, that is what it becomes. Your PB approaches 1 minus rho. So whatever, or right, how can rho is now still large? No, that is not correct. Okay, PB goes to 1, but your lambda 1 minus PB approaches mu. That's so. mu, it will equal mu because it becomes a balanced system. Arrivals equals will equal departures. In all other cases we are seeing arrivals are less than departures.
It is equal to mu or it is equal to L, sir, effective arrival rate. When system is
Have an effect. It is like this key queues are always full.
So as soon
One
as the
packet will serve, only one will be allowed to enter.
So, yeah, so every time a customer departs, another customer is added, and
Yeah.
the departure rate is 1 over is mu. So the addition is also mu.
So it is equivalent to number of servers or service time, sir. You are equating.
This is only one server we are looking at. Yeah.
Okay.
As soon as see at what rate do customers leave the system?
Yeah, that rate
Service
only it
rate
can reach.
is your equals your effective arrival rate, not your lambda. Effective arrival rate becomes
Mu.
mu. So questions on this. So now my graph here makes sense, right? So therefore this becomes P by mu. That's how we get. If then your lambda will keep decreasing, right? So or your rho will keep decreasing. So that then in that case, yeah. So here, yeah, okay. You are saying that in my graph, okay. So let me put that clause there. If so if you fix your rho or lambda rather, and then keep decreasing your mu, you will see the same thing. If your service rate keeps on decreasing for the same arrival rate lambda, right, just going the other way, that is all. Your rho will keep on increasing and ultimately you will for whatever value of mu that you are looking for, right. Each time your mu is going to be varying.
We don't assume that we assume that always mu is fixed, right?
No, in this, yeah,
What do you
yeah,
ask?
yeah, but it could be that,
What did you ask?
yeah, or
Mu
some
is
just for analysis cases. Let us say you know that customers are coming at 1000 customers per second, right? That is known. You are trying to find the appropriate customer capacity, service capacity, right? That how should be the, like buying a machine for example, right? One of the sample exercises that I gave was one copier can print at 10 pages per minute, or a printer can do, another printer can print 20 pages per minute, right? And you are trying to find out what is optimal. You want to reduce the waiting time to something that is acceptable. So in that case you want to keep that lambda fixed but vary your mu so that you find it some optimal mu. Okay. So any other analysis that you want to do on this MM1B? You have seen how anything else on MM1B? No. So usually the I said we do it the other way, right? So given some target probability, how do you determine the value of B? Right? That's the more interesting thing. So for that same scenario, lambda equals to 100 and say mu equals 200, right? So if I set my PB to be something, say I do not want to miss any more than 1 in 100 packets, right? What was the PB that did we calculate PB in the other case? We did not. So let us say we will make it 0.05, right? Yeah, what should be B equal to? So this is a typical router design problem, or in general any queuing problem, right? Capacity design problem. How much capacity should I have in the system, given that the rates of arrival departure are fixed, but I have to meet some target probability. I do not want to lose any more than that, right? It should be less than or equal to, but anyway, if I say that, I do not want any worse than that. So is that a closed form solution, or do we have to need iteration for that? So you go about by right, so rho equals 0.5. B should be greater than or equal to 3.3. So you need at least 4 buffers in the system if you want to meet this target, and this is right straight solution. So you just replace rho B by whatever x and then just plug it in, you are done. We do not have to elaborate on that. So that is where this can be handy. This is of course a very simple system, right. What we really have in routers and all, it is much more complicated than we have a series of routers, right. If you look at this from a delay or buffering buffer allocation perspective, then it is not that easy, but you can have some sort of estimate for every router and say on each router I am going to have this kind of design.
Suppose we have more than one servers.
Yeah.
Then your effective arrival rate will get divided.
No, effective arrival rate of the queue is still same lambda. There is only single queue.
Yeah.
It's a single queue system, not a multiple queue.
Okay.
And when we are calculating this buffer size,
Mhm.
So that is the total amount of buffer or buffer for each
This is
server
the
will
total
separate?
number of customers in the system. So 4 minus number of servers. In this case, there is one single server.
Okay.
If it is more servers, then we will have to actually solve it a little more. The solution will involve, if it is MMMB,
Yes.
then that is more work that has to be done. Right.
So in actual router you have suppose let's say 4 interfaces
Mhm.
and each one of them has got queues.
Yeah.
So we have each independent cards taking care of the servicing of
That
each.
is
Yes,
that
okay.
is
And then you have
one
switch
only.
fabric which does the switching.
Yeah,
That is
that's
one
correct.
MM1.
So, so the buffers can be on the line cards. It can also be right. So this is so if you are doing simple output queuing or even input queuing. This is output queuing is what this is actually used for, right? We saw that last time. If it is input queuing, then it gets a little bit more complex. We sometimes just pretend for analysis sake. What if this were an output queue? Look at the total arrivals to that particular line card, output line card, and then look at the service rate of that line card and then do the dimensioning based on that, right. And this is also not dimensioning only for the router, we are also worried about dimensioning per flow. It gets even more complex, right, because one link is shared by multiple flows, then how much do you buffer do you assign, right, and that is what our buffer design group will know more about, right, the guys who do the buffer allocation.
model each output card has one MM1.
One
I know,
BQ.
but when the output card is shared among multiple flows, then how do you decide for each flow how much? So I have a total of 1000 buffers available on a line card, right?
Total flows will ultimately give me one poison flow only, sir.
Yes, but if the number of flows are varying, then do you just allocate everybody 20 flows or do you give them 20 buffers, right? Is the number of buffers fixed on a per flow basis? Then you will always have overflow at that time too, right? You may certainly see a surge in flows. You won't necessarily see a surge in number of packets entering the buffer, but the number of flows entering will be large.
But if I have got like equal division among flows, then I can just model it as MM1B.
If it is equal division and you are doing round robin allocation, then it will be MD1, this server with vacations. That's a time division multiplexing system. We will look at that variation.